Okay, give you a moment to copy this down. We were talking about section 13.3, the fundamental theorem of line integrals last time, and we're going to do another example here, and you're copying the example down. Okay, so here we're told that our force field is a conservative force field. Okay, so that means that we can find a potential function f of x, y that we can use in our fundamental theorem of line integrals. Now, of course, when we have a two-dimensional vector field, in section 13.3, you learned about a theorem that told you if that vector field is conservative or not, because naturally we don't want to try to find a function whose gradient equals the vector field if the field's not conservative in the first place. So for two-dimensional vector fields, you have a theorem that you can test out before you go after the potential function, before you try to find the potential function. For a vector field in three-dimensional space, there is a way to see if the vector field is conservative or not, and that's by computing what's called the curl. I want to say this the right way, the curl of the vector field. But that's section 13.5. We'll get into that. But for now, all we want to do, we're told we have a conservative vector field, and we want to find the work that this vector field does in moving the particle along the curve C, given by the line segment from 0 to -1 to 5, -1, 1. Okay, so the approach is going to be like the approach you learned. Excuse me. It's just like the approach you learned on Tuesday's class when we found a potential function for a vector field of x and y. Now we're finding a potential function for a vector field of x, y, and z. So, okay, let's go ahead here and we'll look at the solution. So since our vector field is conservative, we can find this potential function such that the gradient of the potential function equals the vector field. Okay. And in order for the gradient of the function to equal the vector field, that's going to require then that these equations 1, 2, and 3, be satisfied. Let me give you a moment to copy up to there. And please let me know if you have any questions. All right. So, all right. So we have to, again, the potential function is a function whose gradient is equal to the vector field. And so we set each component, the I, J, and K vector components of the vector field, we set them equal to the partial derivatives of f, respectively. And so now we have to start somewhere. So let's pick the first equation. We could have picked any of the three equations, but the first equation, the partial derivative of f with respect to x equals y squared, looks the easiest. So what we're going to do is we're going to integrate that equation with respect to x. Well, the integral with respect to x of the partial derivative of the function with respect to x would just give us back our function. So the function x, y, and z will equal y squared times x plus a function g of y and z. So we want to write down the most general function possible. And for this function, if you differentiate that function with respect to x, that partial derivative will equal y squared. Okay, so you always have to put down the most general function. Okay, so now what are we going to do? What are we going to do with this equation? Equation 4. And we number the equations so that we can follow our work, so that I can, follow your work and you can follow your work, and just to help keep things, organized. What do we want to do with this equation 4? That's right, Robin. We want to differentiate that with respect to y. Absolutely. Okay, so we're going to do that. May I move to the next page? Is everybody done copying this page? Maybe give me a few thumbs up when you're ready. Okay, Robin's good. Eric's good. All right. So here we go then. So I rewrote the f of x, y, z function down again, and I'm going to differentiate that function with respect to y. So the partial derivative of the function with respect to y would then equal 2yx plus the partial derivative of g with respect to y. It's not gy, it's not this. It's not, in other words, dg dy. Okay, let me rephrase it. This here is not equal to g prime hold on. This partial derivative of g with respect to y is not equal to g prime of y. They are not the same. Okay, this is a partial derivative, okay, of a function of two variables. So you want to be careful with your notation and not put that there, right? This is the correct notation at this juncture. Now what we're going to do is we're going to compare then the second equation which was the partial derivative of f with respect to y equals 2xy plus e to the 3z. We're going to compare that with this fifth equation, and that's going to tell us then that the partial derivative of g with respect to y and z equals, I'm sorry, it's going to tell us that the partial derivative of g with respect to y equals e to the 3z power. Okay, let me stop for a moment. Let me know if you have any questions. Okay, well, so now what we want to do is we want to integrate this partial derivative with respect to y. Okay, because we want to know something about, I mean, the g function. So remember what, well, actually I can go up here. Remember what our function, hold on here. Remember what our function, sorry, hold on. Hold on. I mean, this here is our function, our potential function, but we don't know specifically what it is yet because we have to figure out what this g of yz function is. So we're doing what we need to do to discover what that g of yz function is. Well, okay, we know that the partial derivative of g with respect to y is equal to e to the 3z. To learn about g, what we have to function g, we have to integrate then that equation 6 with respect to y. And when we do, the antiderivative, we'll get g, function g of y and z equals e to the 3z times y plus h of z. Okay, and h of, and again, if you take g and differentiate that with respect to y, you will get back e to the 3z power. So we have to write down the most general function we can write, and that's what we're doing here. And now, okay, you know, it's like you know, what's this function g equal to? It's a mystery, right? Well, we're breaking down the mystery. We're getting closer. Now we know that the function g equals e to the 3zy plus h of z. Okay, we're breaking that function down. Okay, well, now here we're at equation 8. What would you recommend we do now? What would you recommend that we do? What would you recommend? Have we used the first 3 equations, those partial derivative equations, have we used them all yet, or is there one that we haven't used yet? That's right, Robin. We haven't used the third equation involving the partial derivative of f with respect to z. So what I'm going to do is I'm going to differentiate this function with respect to z. Okay. Are there any questions before we move forward? Okay, well then let's move forward. I'll differentiate that equation with respect to z, and this will give me then equation 9. And in this case, the h prime of z is a regular derivative. That's not a partial derivative, because when we differentiate h of z with respect to z, that's just a regular derivative. Okay, I'll stop there for a moment. Okay, so now what we're going to do is compare equation 9 with that equation 3. I'll go, remember equation 3 was this equation here. Okay, so we're going to compare equation 9 with equation 3. And when we do so, h prime of z is going to have to equal 0. That's what h prime of z is going to have to be equal to. And therefore, h of z would equal k. And now we've identified our potential function. And I like to leave the k there, but you can set k equal to 0 if you like. Okay, you can set k equals 0 if you like. Okay, so now we have our potential function, and we can compute the work that the particle does in this three-dimensional space. I'm sorry, we can find the work that the force field does in moving this particle in three-dimensional space along that line segment, along the line segment. And, you know, again, if you're using section 13.2, if you were to compute the work using section 13.2 line integrals, you'd have to get the parameterization for the line segment. And of course, if you don't have a conservative vector field, then that's what you have to do. Okay, but at least, you know, we do have a conservative vector field, and so it's tremendously helpful. All right, so are we ready to go to the next page? Who's feeling comfortable so far? Okay, Eric is, excellent. And Robin is, good. Okay. Well, then let's go ahead to the next page then. Fundamental theorem of line integrals. So remember now, the gradient of our function, and this is the function right here. The gradient of that function is equal to our vector field F. Okay. So, okay. Well, by the fundamental theorem of line integrals, which we proved in the last class, says that the integral of the gradient dotted with the dr vector over a curve C, and again, that stands for work, that is equal to the difference of the function values where the particle begins and ends. And remember, that's only for, well, no, that is the fundamental theorem of line integrals. So since our vector field F is equal to the gradient of a function, you know, since the vector field F is the gradient of our potential function, then by the fundamental theorem of line integrals, FTLI, the work done by the vector field F in moving a particle along that curve C, given by the line segment from 0, 2, -1 to 5, -1, 1, that's going to be computed as you see below. So let me give you just a little time to copy this down, and I'll see if you have any questions. Okay, so I tried to show here, so I'm applying the fundamental theorem of line integrals. So for again, this here is the work that we're trying to find, but we're able to replace the vector field f with the gradient of f, and so we can apply the fundamental theorem of line integrals. We know what the function f is. We evaluate the function at the beginning point and the end point, okay, of that line segment. And I tried to, like -1 squared times 5 is -1 is y squared times x, and then e to the 3 times 1 power times y is e to the 3z times y. So I'm just trying to put that in because the hold on here, the function the potential function was equal to y squared x plus e to the 3zy plus k. And so I just wanted to kind of, justify everything. The k's cancel, and this is going to be your work right here. Are there any questions on that? All right, I'm going to ask you a question because I'm in the neighborhood here. What I'm doing is I'm drawing a line segment. We'll call it C1. And the line segment, of course, is the line segment, our line segment. It starts at, maybe I'll put this in black. It starts at point 0, 2, -1, and ends at point 5, -1 and 1. Okay, and we are going in this direction. Okay, now what if this problem said, find the work done by the conservative force in moving a particle along a curve C defined like this. What if instead that were your curve C2? Would the work still that the force field does in moving the particle from the point 0, 2, -1 to the point 5, -1, 1 along this different path, C2, would it still be equal to the work given by 5 minus e to the third power minus 2 times e to the negative third power? Would the work change, or would it be the same? That's right, Robin. The work would be the same. That's right, Christopher. The work should be the same. And again, it's because of the way we computed the work. By the fundamental theorem of line integrals, and the fact we had a potential function means the only thing that matters is the value of the function at the beginning point and the end point. It doesn't matter what path you take to go from the starting point to the terminal point. Okay, that's called independence of path. And that's true for when we have a conservative vector field. All right, are there any questions? Any questions on that concept there? All right, who's comfortable? Who's comfortable? I'll end the recording, but who's feeling comfortable here? Maybe give me a few thumbs up if you're feeling good. Okay, Marvelous is good, and Robin and Christopher, excellent, excellent. And Eric, wonderful, wonderful. Okay, let me stop the recording here.